Okay, I assume everybody can hear me. I'm not muted. I'm recording. Got my chat up. All right. Yeah. Bad news for me. I got Omicron. I'm kind of but I want to do lecture today because I don't want us to lose time, but I'm a little bit under the weather, but it's not as bad as it was like late last night. They say Omicron is mild, but that did not feel mild. I got stomped. I got stomped hard by that thing. So anyways, I'm still feverish, but I'm not delirious like I was. So anyways, I hope that I'm coherent in the lecture here, but yeah, we gotta move on here. So, okay. So if there's any questions, just put them in the chat. I'll release recitation number 4 today, which is normalization, normalization recitation. Okay, so where were we? We were at 3NF. And 3NF, you can always preserve all dependencies. The kind of the core, like the simplest 3NF is just this: is AB goes to C, and C goes to B. So this is kind of your prototypical simplest. It's true, right? Yeah. Okay. One second. Sorry. Okay. All right. So this is your kind of the simplest case. And this pattern comes up quite a bit, but usually it's kind of a bit more complicated than that. So anyways, the 3NF, the algorithm to actually get a 3NF decomposition is called the synthesis algorithm. And it's basically characterized by going bottom up, as opposed to top down. So the BCNF decomposition algorithm, that was top down. And you guys are going to be given like a set of these. Yeah, I mean, doing the BCNF decomposition algorithm and doing the 3NF decomposition algorithm, synthesis algorithm. The recitations, you're going to get a bunch of those. But let's start out. Let's just do an example here of 3NF. I just kind of cooked up an example here. I hope it's not like a degenerate example, which kind of breaks, but basically you could just kind of B goes to D. All right. So and let's just do this over the relation A, B, C, D, E, F. Notice here how F is not mentioned in any of these here, but there's nothing that says we can't do that we can't have that an attribute needs to be mentioned in some kind of functional dependency. It can be sitting out there kind of separately. All right, so how does the decomposition algorithm work? Okay, step 1 is to I'll just put the steps right here. Step 1 is to put FDs, functional dependencies, in canonical form. X goes to script A. Okay, so we want to put these into a form where we don't have any sets of attributes on the right-hand side. All right, so that's canonical form. All right, this canonical form. So that's the first thing we do. So that's actually pretty easy to do. It's just AB goes to D here, and I'll just put it in that. Okay. So I mean, this is a really easy algorithm. It's really easy to kind of do this. So now what we want to do is number 2 is calculate a minimal basis. Minimal basis. All right. So what this means then is this means that what we're going to do is we're going to basically we're going to ask ourselves, are any of these functional dependencies redundant? So in other words, this is big F right here, right? So this equals that's just like the set of functional dependencies. And then the question would be, is F plus, what we want to do is we want to basically have it. So can we remove any of these and still have it so that the F plus is the same? So in other words, there's no redundancy in these statements. Okay. So the way you do that is you basically would say something like this. You'd say AB goes to C. Okay, so first you would do is we would consider this one here. AB goes to C. We're asking right here, AB goes to C. Can we derive AB goes to C from all of from these other ones, from these functional dependencies? So do these functional dependencies here, do they, using Armstrong's axioms, can we derive AB goes to C? Okay, so AB goes to D, doesn't look like, is C on the right-hand side of anything here? No. So intuitively, I can kind of say that I think this one's going to survive. All right, so what we're doing here is we're calculating what's called a minimal basis. Okay. Now, next thing is we'll go to C goes to E here. All right, now, so we're done with this one. This one has checked off. This one is going to make it into the set. Now, C goes to E, C goes to A, but I don't see E on the side of anything. So I think this one right here also is going to wind up surviving. Now, E goes to A. Let's see, C goes to, E goes to A. Can I derive E goes to A from the rest of these guys here? Well, C goes to E. I don't think so, because E is not on the right-hand side, or not on the left-hand side of anything. So I don't think I'll be able to get E goes to A from the rest of them. So this one I think also checks out. Now, C goes to A. Can I get that with the other ones? Can I get that with the other ones? Well, via transitivity, if C goes to E and E goes to A, then C goes to A. So therefore, this is redundant. This is not, we can get rid of this. Okay. So that's no longer necessary. Now EB goes to D. All right. Now EB goes to D. Okay, AB goes to D. E goes to A. So the question would be this, is that E goes to A. Can I get EB goes to D? Is this redundant? Let's work on that a little bit. So we're gonna do that to the side here. Okay, E goes to A and EB goes to D. AB goes to D. Okay, so maybe I would say this. AB goes to D. If AB goes to, so basically, this is the one that's under question here, is this one here. If AB goes to D, then and E goes to A, all right, so E B goes to A B. Is that right? That's right. Now the reason why can I do that? Why can I say EB? Let's see, what was the answer? Yes, there. Is that like, yeah, that is redundant. That this is redundant. Okay. EB goes to AB. That I get that by just the simple augmentation rule of Armstrong's axis, because E goes to A, right? Yeah, E goes to A, so I can enrich both sides with the B, right? So now I have EB goes to AB, and I have AB goes to D. Therefore, via transitivity, EB goes to D, right? So therefore, I was able to use these other ones to actually derive that one. So this one is redundant. Okay. All right. Now AB goes to D. I don't think I can get that through anybody else because AB goes because nothing else has D on the right hand side. So, so that's this is done. Okay. Was the argument? Yes, this is an algorithm where we took these input functional dependencies here, and excuse me, and we want to do a 3NF decomposition. Because notice what we have here is we just have the function, we just have the attributes up here, and we have the functional dependencies that govern the domain, and we want to come up with a set of table definitions. So that's what we're working on right here. And I think we're done now with step number 2 here. That is, we've calculated the minimal basis. Okay, step number 3. That is that step number 3 is we basically group FDs by same left-hand sides and merge into tablies. All right, so we have 4 functional dependencies that have survived. Now, if we group them by the left-hand sides, that means that this one here, this AB goes to D, and AB goes to C. Those become one group, and C goes to E, and E goes to A becomes. So we have 3 groups here. We have AB, we have C, and we have E. Right. So AB has 2 functional dependencies that is represented by. And then when you do that, what you do is you wind up merging. So basically, I take these 2 functional dependencies for AB, and what I do then is I basically say R1 is going to be AB, that's the left-hand side there, and then C and D. Okay, so that's our first one. And we know, by the way, that this is the well, AB is the superkey of that because locally, by definition, this would be superkey of that. All right. Now, then we do the same thing here. We say R2 CE, and we know that that's going to be the superkey, C is, and R3 is going to be E. Okay, so this is, this is going to be, these are going to be three of the tables in our decomposition for these functional dependencies. These are going to be 3. However, there's one final step. That is that basically introduce relation with candidate key of R, universal, if needed. Okay, so let's go back up here and let's say, could people give me the candidate key? So given, now we only have to look at these 4 right here. What is the candidate key of R here? What's a super key? Again, A, B, C, D, E, F is a super key. So give me a minimal super key of this, that relation there. Oh. Sorry, I should keep my putting that away. AB. With AB, can I get everything? With AB, I can certainly get CD, and then I can get E, And then I can even get A again, but I don't get F, right? ABF, yeah, there we go. I think ABF. ABCDF is not a candidate key because it's not a minimal super key. ABDF star, what the star is for. But ABF, I think, is a candidate key. ABF, because with AB, I can get all the other ones, then I need F as well. So what that means, it means that we're going to have an R4 here, which is going to be ABF. Okay. And this is essentially the key that here. So, oh, okay, I see. Oh, ABD. Oh, I see. Maybe ABD. Yeah, AB goes to D. Yeah, the bottom, exactly. So, so the decomposition, the total answer to this thing right here is going to be this relation R1 with ABCD, R2 with CE, R3 with EA, and R4 with ABF. All right. Now we're going to go. We're going to cover the chase algorithm for basically lossless decomposition. I'm going to show that in a second here, and then we'll see based on that we'll be able to get we'll be able to show that this decomposition here is lossless. Okay. In fact, maybe I'll go right into that right now. I just want to let's just cover very quickly the chase algorithm. It's very, very simple, actually. It kind of works the following way. Let's say that I have the following relation, universal relation, ABCD. Okay. And then let's say that it's governed by the functional dependencies. A goes to B, C, and C goes to D. Okay. Now, if we were doing that, now the question would be right here. It's like, is this in BCNF? Is this in BCNF? God, it's getting bright again here. How'd that happen? One sec. Maybe better? Is this in BCNF? No, that's right. And the reason why it's not is because this one right here, C, is not a superkey of this relation, right? Yeah, exactly. Very good. Let's look at this right here, and let's just ask ourselves the following question. That is that if we want now, if we use the BCNF decomposition algorithm, what we'll get is we'll get R1 A B C, R2 C goes to D, CD. Okay. So now let's just verify something. Let's just do the chase test here. What's called the chase test. Let's do the chase test to verify, and I'll show you kind of the criteria here. It's like a little simple kind of plug and chug to verify that this is lossless. Okay. Here's how you set up a chase. You first you write A, B, C, D, and then for each of your relations here, you write in basically the way you do this traditionally is basically you'd say something like alpha A, alpha B, alpha C, beta 1, comma D. Okay, and the reason why this is for R1 here. So what you're basically saying is you're going to say alpha A, alpha B. That's a B. Sorry guys, this is a little bit small. Alpha A, alpha B, alpha C, because those are the A, B, and C that are represented here. And then we're just going to have beta 1 D here. So it's like just kind of like we don't know what it is. It's not, we don't have that. It's not dealt with yet. Okay, then we have R2 here, and R2 is going to wind up having alpha C because it's C and D, and alpha D. Okay, and then this is going to have beta A2 and beta B2. Okay, so maybe I can write a little bit larger, but anyways. So the idea here is then what you do then is now you can apply the functional dependencies here.
So if they match on the A here, so alpha sub A and beta sub A2 are not the same. So you can't match those. But C goes to D, you can match those. Alpha C is equal to alpha C. And so then what that allows you to do is it allows you to basically cross off and put in alpha sub D here. Okay. Now you just kind of do this as long as you can. That's why they call it chase algorithm, because it's kind of chasing things around. You do this as long as you can. And if you can generate a row that's all alphas, then it's basically a lossless decomposition. Okay. And this is a sound incomplete algorithm. So sound incomplete meaning that it's always going to identify, if it says that a decomposition is lossless, then it's lossless. And if a decomposition is lossless, it's going to say so. So it's both sound and complete. So it's a good algorithm, right? So let's just do another one here, just to kind of let's say that I had a different decomposition, and it was R1, and it was basically A, B, D, and then I say R2, and R2 winds up being we can say R2 is in CD. Okay, now this one here, I think we're going to run into some trouble. Let's do the algorithm for this one here. Excuse me. I'll just use this above here. So R1, that's going to be alpha A, and it's going to be alpha B, and it's going to be beta C1, and it's going to be alpha D, and then R2 here is going to be beta A2, beta B2, alpha C, and alpha D. Okay. Now, so notice here that we can't apply anything. So we can't apply any of these functional dependencies here. They're not, none of them are going to apply because A don't match and the C's don't match. So we're stuck. So we're not getting anywhere. So this is not, this decomposition here is lossy. And in fact, if you take this and you substitute in constants for these values here, these are all variables essentially. You substitute in constants, and this would actually be the example that you can feed in that will generate spurious tuples. Okay, so just if you just have two rows, you can generate spurious tuples. Right. So this is the chase algorithm. Now, when you look at this chase algorithm, you can see by definition why it's the case that you can see that the chase algorithm, when we do a decomposition where we're basically taking we have a functional dependency x goes to y in RZ, and we're basically breaking it down into R, X, Y, and R, Z minus Y, right? That's what this is R prime and R double prime. This is kind of what this is in our decomposition algorithm for BCNF. This is not a super key. X is not a super key, so we have to break this up into these separate relations here. But if you look right here, what you'll see here is you'll see that, well, based on doing that, that the chase, just by looking at how the chase operates, you can see that this is going to always generate a lossless decomposition. Okay, you just kind of you can work a proof to see that, to see why that's the case. But if you look at it, it's like X is in this right here because it's Z minus Y. So X is in there, and then X is here, and then X is a key here, so it's going to propagate over. So we know it's going to be lossless, right? And then likewise, in our 3NF decomposition, since we're going to have a relation that contains the candidate key, from that relation that contains the candidate key, we can apply the chase to basically generate a full row of alphas. Okay, so so the chase is the chase algorithm, and we're not going to prove the chase algorithm why it holds, but this is the kind of mathematical basis for why these algorithms we have here are generating lossless decompositions. And also, if you notice here, if you look back at this algorithm here, because you compute the minimal basis, and every single one of these functional dependencies here have some kind of happy home in some relation, because the relations are built upon the functional dependencies, and these are a minimal basis, so all the functional dependencies are represented here. Based on that, we know that it's going to be dependency preserving, right? All the functional dependencies are going to be reflected. Okay. All right. All right. So, are there any questions about this? Excuse me. God, I really hope that tonight is not as bad as last night. But I don't know, maybe Omicron. I mean, I have a positive Omicron test, so I have Omicron. So you guys should be glad that we're doing this over Zoom and I'm not sneezing all over the place in lecture hall. All right. Do I have any questions here? All right. What do I want to do now? What I want to do now is I want to kind of, before we go on to what's called multi-value dependencies, which we're going to kind of, we're going to cover multi-value dependencies. But let me just do that in a little bit. I just want to, I want us to kind of like get a sense of kind of what's really going on here. And based on that, I want to just kind of develop an example here. And I want your help on developing this example. All right, so I mean, I don't play video games because I don't have the time to. I've got other things, but I do at least kind of like see some of them, and I okay. Well, I have this video game, but I don't play it because I don't have the time. But it's called SnowRunner, and it's about trucks and deliveries of packages and stuff like that. So I'm not sure if anybody knows and has ever seen SnowRunner, but we're going to kind of do a little bit of a model of SnowRunner. And so in SnowRunner, you have trucks and you have trailers, and then you're basically delivering cargoes from source places to destination places. Like you might deliver like a cargo of a bunch of steel beams to a factory or something. So you pull the cargo. So we're going to do like a little logistics example here of trucks and cargoes and trailers. And then we're going to see how far we can develop this. But let's start out here with just some symbols here. So we have the notion of a place. All right, so a place is just going to be a name, like for instance, like the sawmill, or like the farm, or something like that. So this is, I mean, okay, a place, and then we have a truck ID. I always call it T for truck ID. All right. Now a truck ID is like, it's not like a fleet star. That's a truck type. So let's do that as K. Truck kind. And notice we could also do all the upgrades and all the different kind of things, like you get like a special winch for your truck and stuff like that. But anyways, so we have a truck ID. So this could be, for example, truck 55. And this right here could be fleet star. I can't remember the number, but the fleet star, I think 1141 or something. So this is like, a model and make of a car, or of a truck. All right, let's keep it real simple here. So for instance, we're not going to deal with trailers quite yet. We'll just deal with trucks for the time being. So we have a place, we have a truck, and then of course we have I'll just call it D, we have a timestamp. Okay, so this is just time. This is space. This is a particular truck. This is a truck kind. Then we're going to have a cargo kind. I'll call that B. And that could be, for example, steel beams. And then we have a particular cargo. So this could be something like cargo 1141 steel beams. Okay, so this is an instance of cargo, right? It's a package of steel beams. This is just a type in the notion of a steel beam. People follow this? Okay. So I ask you, what functional dependencies are governing this domain? Is there anything that we can, is there anything we can pluck out of this? I mean, you guys, I hope you guys understand what we're modeling here. We're modeling trucks delivering cargoes. Trucks are going to be delivering a cargo to a place and time. Okay, TK. All right, so we got TK. Truck ID, truck kind. Absolutely. Yeah, so we know we have T goes to K. Right, so one particular truck, like this truck 55, 551 maybe, that is a fleet star. Right, so trucks have particular kinds. That is true. Anything else? A goes to B. A cargo has a kind. Yeah, cargoes have kinds as well. A goes to B. Right. Excuse me. Anything more? All right. Truck goes to DP. So a truck ID goes to a D and P. I think you're close, but I don't know. Wait, maybe, okay, D implies, all right, so you guys are, you're getting closer here, but not, these aren't quite right, because a truck determining a date and a time, a date and a place, that's not, I mean, I think maybe the inverse could work. So if you give me a particular date, and dates, by the way, are timestamps, so this is down to the second. And we say place may be like a XY coordinate. This is a little bit, it breaks out a little bit. But you could say something like, if you wanted to say that at a particular place and time, wait, one second. At a particular, wait, D goes, okay, at a particular place and time, there can only be one truck. That's probably true, right? If the places are down to XY coordinates, you can only have one truck sitting on that position at that particular time. Is that true? How do I represent that? Let's say that it is true. Let's say we want to represent the fact that a truck, I'm sorry, a place and a time. So this particular part of the driveway at that exact coordinate, at this exact moment, there can be only at most one truck in that place. How would I represent that? Right. Okay. So basically, the timestamp and the place give us the truck. That's right. Are there any other ones? Now, I just wanted to say one thing, and that is that in this particular model here, I want to say that the cargoes are basically, it's very simple delivery mechanism. Cargoes move on one and only one truck. So the actual cargo, like this cargo 1141 SB, which is steel beams, that is going to be associated with at most one truck, and the truck that made its delivery, right? So we're basically dealing with a model here where cargoes only get delivered by a single truck to a single place. How would I represent that as a functional dependency? If I was going to say that's the case. Truck, I think you got it reversed there. So truck, so one particular truck can have many different cargoes it's delivered. But any particular cargo has to be only one potential truck. So remember, the cargoes are just packages. They're not types. They're packages. So I think you're close here. I think that, well, what's that here? Oh yeah, there we are. What yeah, exactly. A determines T. That's right, exactly. A determines T, right? Because the cargo determines the truck that it's going to be delivered. Now, this doesn't mean that every cargo has to be delivered. It just means that a cargo is going to be associated with at most one truck. Are there more? Can we dig out more in this example? I mean, you kind of go through these things and say, like, what do we have here? Is it true that a truck at a particular moment in time determines a place? Is that true? I think it is. So how would I represent that? So truck at a particular moment in time would determine a place. Yeah. So DT goes to P. All right. I have to go turn off that stupid robot. One second. Is there a way to determine the place and timestamp for when and where a certain cargo should be delivered? A determines. Oh, A determines D and P. I think actually that's a good question I see there. The order of D, by the way, the order of DT and TD does not matter. Somebody asked that question. I mean, these are sets. So it's a little bit tricky, like when you do this kind of modeling, when you're doing it this way, if you're talking about like, if you want to talk about like, I think that what you want to do, so there's a question here, is there a way to determine the place and timestamp for when and where a certain cargo should be delivered? It feels a bit off to say, yes, that's right. So because the thing is that what you would want to do to handle that, which you certainly could, is you would want to have something like, say, delivery destination. So we want to introduce we could say like E is destination, and then F is delivery time. Okay. So adding those in is probably the way you'd want to handle that, because you're introducing kind of new attributes. All right. So a cargo would determine the destination. So A would determine EF here. Right. Is that right? Yeah, that's right. A would determine EF. Yeah. So I mean, there's a little bit of an art to it, but that's really interesting, kind of what you brought up, like that, bringing up that kind of like extension of the model to kind of cover that. So what I'm trying to get to here is this, that we could have done this same thing with entity relationship, right? We could have tried to model like like trucks and places, and anyways, I mean, we could do it that we could do it that way. But if we're continuing on with this right here, the question is, are we done yet? Are we done? A truck kind determines. Does that determine anything? No. Does a cargo kind? Does a cargo A gives us kind, A gives us truck. This might be complete here. So what you would do now is you would take this, if you just stuck with these right here, you would take this and then we could maybe like do the 3NF decomposition of this thing here. Is this T goes to K? Does that looks like that's legitimate? Right, that looks legitimate in terms of like surviving. It's nothing else. Is that A goes to B? That looks legitimate. DP goes to T. DP goes to T. DT goes to P. I think this is fine. Is that right? Can I get the other one? Can I get DP goes to T? I think this is fine. A goes to T. I don't think I can get that through anything else. DT goes to P. Now maybe that I can get. If DP goes to T. No, because that's going to be place. Yeah, I think these all look kind of legitimate. So then we would say something like, all right, now, given these right here, could someone just please give me P, T, K, B, could someone give me a candidate key of this thing? Meanwhile, I'll just kind of do the grouping here. So that means that we're going to have, if I group these guys together, then I'm going to get A, B, T, and that's R1, T, R2, D, P, this one here, T, R3, this one here is DTP, okay. And then we got TK here, right? R4 is T. Okay. Now notice here, R2 and R3 derived from here and here. These are the same thing, right? Because it's the same set of attributes. So we can get rid of one of those, right? Because it's the same attribute. I mean, it's the same attributes. So we never have a table that had both those. So the question now is ABT, is that a, all right, did somebody calculate the candidate key for this guy here, given these? Is, I mean, it looks like it has to have A in it. Any candidate key needs to have A. You can see that. All right. Oh, and then let's see. What else does it have to have? At least looks like it needs to have T here. Anything else? Let's see. All right, guys, we'll go to break once we get this thing done. Can we get T from A? Yeah, A goes to T. I mean, oh, right. Okay, so that doesn't, what am I talking about here? So we have A, we know we need to have A in the candidate key, right? So with A, we can get T, what else? And B. Okay. And then what else do we, with T we can get, and then with T we get K. And then with D, do we get D? No, we need D. So we need D as well. A and D. And with D and T, we get P. So AD, T, let's see, 1, 2, 3, 4, 5, 6. 1, 2. So is AD, is that right there? Is that a candidate key? Or D? Is D or A? It seems to me that AD, cargo, and timestamp, that's kind of weird. All right, I'm going to look at the, excuse me. I'll play around a little bit more with this in and break. But the thing is, I mean, we're just kind of seeing what pops out of this thing. A is cargo, and D is timestamp. Okay, cargo and timestamp. I wonder if we can get one sec. No. Well, if we just take it at face value here, we need to have this other relation here, R5. I'm not really sure how intuitive that sounds very strange. Cargo plus timestamp. Cargo timestamp. Why would that be weird? Is that AD? Is that really cargo? Oh, that's right, because they'll give us the truck. This seems like it might have degenerated a bit. So we'd have to kind of fiddle around with this. We might actually go instead say maybe we should do a BCNF decomposition of this. We would see. The point is that this is but just this whole business of going through and kind of determining these functional dependencies, it kind of gives us an alternate way, and kind of a bottom-up way to do the modeling as opposed to like more the top-down entity relationship. So I mean, kind of got a little bit kind of quirky there. We have to kind of look at it. So, this is these things a lot of times, you work with them and then you kind of say, well, but that's not quite how I want it. Like, I don't want to define that table because that doesn't make that much sense. It doesn't have that much intuition about it. I mean, one of the dangers of normalization theory is you can come up with definitions that don't really have good intuition backing them. It's just kind of what the theory guided you to declare, and that would be problematic. But I mean, I've seen it before. I've seen really highly normalized relations where it's like they don't really understand why, but just kind of plopped out of the theory, and it kind of works in practice. But you'd want to kind of have it so these are kind of more intuitive, more based on entities and relationships. So, but both analysis paths you might want to look at as you're deciding how you're going to define the database. Okay, guys. Well, let's come back at 20 after. We're not going to actually need the full hour, and I don't really know how much. I mean, we're going to cover multi-value dependencies, and I'll take some questions. I guess one option is we could just muscle through right now, but I suppose people want to have a break, and I think I might want to have some coffees and take a little break myself. So, okay, let's get back at 20 after. All right. So hopefully we can get this done fairly quick. I need to sleep. Anyways, I want to introduce the following simple example. So in entity relationships, we didn't cover it, but you can have the idea like person, and then you can have, well, of course, the ID, which is the key. And then you can have what are called multi-value attributes. So you could have something like favorite colors. Okay, so green and blue might be the favorite colors, or just green or whatever. And then you might also have like favorite ice cream. Chocolate, vanilla, strawberry, whatever. So we covered, but these are called multi-valued attributes. So this is the idea of like a set. So it actually kind of goes against the relational model a little bit because, relational model is under first normal form where everything's atomic valued. But let's represent this in a table. And what we'll see here is actually that we're going to lose the ID here a little bit, but let's just go with this. Let's just say name. All right. Let's just consider the following table. So, person. And then color, ice cream. All right. So if I say, let's say that my favorite color is definitely green, and my favorite ice creams are strawberry and chocolate. All right, and let's say I'll also say that I like the color blue as well. All right, so I want to basically show that Mike has favorite colors of blue and green, and ice cream is chocolate and strawberry. Okay, if I want to do this in a table, here's what I have to do, and this should make everybody kind of like think, ugh, this is weird. I mean, why would I? Well, okay, let's just do it. Mike, green, blue, chocolate, this right here is representing that. Now we can see this looks really strange because there feels like there's this kind of redundancy kind of built into the table. I mean, repeating green twice here, and blue twice here, chocolate's being repeated twice, and strawberries being repeated twice. So now there is no. I mean, what are the functional dependencies that are governing this? There are no functional dependencies that are governing this table. I mean, certainly it's not Mike. That's not functional dependent because that's not determining the color because there's two different variations here. So there are no functional dependencies over this table, right? So then I ask you, is this table in BCNF? There are no functional dependencies, and we have weirdness going on here. But is this in BCNF? I mean, yeah, it's in BCNF. So this shows us that there's like something we're missing here because we don't like this redundancy. We don't want this. Now, an alternative way of doing this, kind of like you might have already kind of anticipated this. An alternative way of doing this is to break this into two tables. One's called color, and the other one's called ice cream. Two tables. Now now, I mean, I hope intuitively, I hope that people understand or feel that this is a preferred, that we don't want to have this kind of weird table where all like the cross combinations have to be encoded because there are set values. All right, we're doing kind of like almost like a Cartesian between the sets within the table. It's something weird going on there. So what we'd really like to do is really like to have it so that it's like this. Right? I hope that makes sense to people. Okay. So this is now this right here. This basically this example, what this is showing here, what we're going to do here is we're going to basically say there are no functional dependencies that are governing this table, but there are what's called multi-value dependency. Now, multi-value dependency, if you look at the slides, has kind of a tricky definition, but it's really I mean, you most of the time you just intuitively write these things down. Like you basically say this. You say name multi-determined. So it's like a functional dependency that's got two arrows on it. Color and name ice cream. So these are two functional dependencies. Now, what functional dependency? I'm sorry, these are two multi-value dependencies. So what a multi-value dependency actually says is it says that basically if I say X multi-determines Y over R of Z, where Z is a superset of X union Y, what this basically says is it says that you can I mean, the technical definition, which is confusing, but is formally correct, says if two tuples agree on X, then their components in Y may be swapped. So if two tuples agree on X, then whatever is in Y, those two can be swapped, and the result will be also in that relation. That's kind of what that's kind of what it's saying formally. But it's I think the intuitive thing is just mostly to say that name multi-determines color. So you're going to have a set of favorite colors, and you're going to have a set of favorite ice creams. Okay. Now, so actually this table here doesn't have any functional dependencies, but it does have name, color, and name multi-determines ice cream. All right. Now, if X and Y, X union Y equals Z, then actually it's what's called a trivial. It's called a trivial multi-value dependency. Okay. And the reason for that is that it's not saying anything at all, because this business of the swapping out and doing duplicates, there are no duplicates to make. So it's always just this is always true. So if X multi-determines Y over the R, which is X union Y, is trivial. It's always true. Okay. Now, we have these two multi-value dependencies, and we have this table here. So this table here is in BCNF, but it is not in what's called fourth normal form. These are in fourth normal form. So let's get a definition of what fourth normal form is, and then we'll be done. All right, fourth normal form is a relation is in 4NF, fourth normal form, if whenever X multi-determines Y is a non-trivial multi-value dependency. Then X is a super key. It has a funny definition to it. It has kind of a funny way it gets applied. Basically, what it does in practice is this is not in fourth normal form because, first of all, name goes to color over this table here is non-trivial. It's a non-trivial multi-value dependency. And X is certainly not a super key. Therefore, this multi-value dependency, as well as that one, both violate fourth normal form. Okay. So what do? We do the same thing we do with BCNF, and that is we do a splitting of the relation based on, this right here winds up being, so X goes to Y here that's X and that's Y. And so this is our X, Y, and this is our X, and then well, minus Y. So this is our X, Z minus Y, which winds up just being ice cream. So we actually do the split exactly the same way we split for the BCNF decomposition. We do that split here. Now, when we get down to here, both of these multi-value dependencies are trivial over their respective subtables. Okay. So based on that, what happens then is this is actually meeting fourth normal form. So these actually right here are meeting 4NF. Okay, so it just gives us, it's kind of, there's a lot of mathematics, there's a lot of logic, and there's a lot of definitions around MVDs. But ultimately, this is what it really comes down to. It's fairly straightforward to apply in practice. So, I mean, a lot of times, like in that example of trucking that we did before, we would say something like, if we introduce something like like compatibility, like certain trucks are compatible with certain trailers, then we would be introducing multi-value dependency that basically the truck type multi-determines trailer types. So I mean, and then you can actually add those in. Now, one thing to keep in mind also, just as a silly little fact, and that is that if X, sorry, functionally determines Y, then X multi-determines Y. All right. So this is one of those things where you can make a lot of statements. I mean, but it's kind of it's a funny example because what it's doing is it's basically saying, yeah, sure, like it multi-determines, but there's only going to be one item in the set, right? But just formally, this holds. So what you'll wind up doing, like if we went back to our trucking example, it may very well be, it's not going to hurt for us to do it, but it may very well be that we would be making, we would wind up making, if we talk about like types and compatibilities of trailers and stuff like that, we might make a lot of multi-valued dependency declarations as well. In fact, you wind up getting a lot of multi-valued, and some of them don't really kind of wind up playing a role once you start doing the decomposition. But it doesn't hurt to make those statements because I mean it's basically you say this thing can be associated with a set of things. Okay, so it's a little bit weaker than saying a functional dependency, but it still says something. So a lot of times the way this engineering works here in conjunction with ER, but you're doing it from the bottom up as well. You'll be making a lot of statements that are multi-valued and functional dependencies. You just kind of keep on making those statements, just so that you can kind of flesh out kind of what it is, what are some of the rules you want to govern, even though the multi-value dependencies are quite a bit weaker. It's pretty obvious that you never would want you would always move things to fork normal form when you actually define the database tables. I mean, you would never leave in one of those. You would never just take it to BCNF, you would go on. So I hope that makes some sense. Are there any questions? So we've covered normalization theory. That's what we're going to cover in terms of normalization theory. There actually is a lot more to normalization theory in terms of like, well, I mean, it got really kind of academic, but there's a whole kind of set of different, like something they call a join dependency. But those are just really academic. They don't have any, as far as I can tell, they don't really impact practice as far as, I think you guys have enough tools to do the practice. But yeah, I mean, you can always learn more things about this kind of stuff. All right, are there any more questions? Are there any questions? Let's ask. Because I'm gonna go to sleep. I'm gonna go take a nap, and then I'll release later today, probably later tonight. I'll release recitation 4, but I'm kind of exhausted right now. So okay, so if there are not any more questions, I will just we'll just end it there. Okay, thanks everybody. The slides should be up. I think I posted those. I mean, the slides are just kind of like notes to this, but I mean, I think the readings are better. The book does a fairly good job of this stuff, but the slides can be, I guess, somewhat helpful. Somebody's asking how long until we can have lectures in school. Actually, I was planning on like coming in next week, but I don't think I can. I mean, I don't think I want to now. I mean, I don't know how. I mean, they say Omicron is mild, but it's not. I mean, at least last night did not feel mild. That was terrible. I got stomped. So I don't know. I mean, I guess the thing is, I might complain about having Omicron, but maybe everybody else has had it as well. But this is the first for me. I got a major headache right now. Yeah, maybe 7 days after or something. Yeah, if you recover. I don't think it's going to take me down. I mean, I don't think the wolf is going to get me. But I was last night though. I was well. I tend to exaggerate these things, but it sucked. I don't know how many people have had this thing yet. Hmm. Yeah, but I mean, I'm sure you guys would not appreciate me being there in person and coughing over everybody. This will be over sometime soon, I guess. It'll just be like the flu, I guess. And that's what the people say. But, I mean, I have a friend who got Omicron and he still can't feel his fingers and his toes. So, I mean, yeah, I mean, I don't know. It's a weird disease. Most likely, I guess they say it was hatched up in a lab. But I'm not gonna. I won't tread into that. I have no idea. I mean, well, that's beyond my purview. Okay, guys. Okay, I'm gonna go sleep. All right, catch you all later.